All right, we're going to solve this system of differential equations. We've already got it written in the matrix form. So we want to find the eigenvalues and eigenvectors of this matrix. So we need to find the determinant of this matrix where we subtract lambda from the main diagonal. So the matrix 3, negative 13, 5, and 1. So we're going to subtract lambda from 3 and 1 and then find the determinant. So we multiply down the main diagonal, so give us 3 minus lambda times 1 minus lambda, and then we subtract the product of the other diagonal. So that'll be plus, looks like 65, right? And then we just need to simplify this, going to multiply this out. So I get 3 minus 3 lambda minus lambda plus lambda squared plus 65. And combine like terms, we get lambda squared minus 4 lambda, and then plus 68. So we're going to set this to 0 and solve for lambda. So it doesn't look like it factors, so let's complete the square. So I'm going to move 68 to the other side. So I get negative 68 equals lambda squared minus 4 lambda. And then I want to complete the square, so I'm going to take the term in front of, or say the lambda term. I need the coefficient, it's negative 4. I'm going to divide that by 2, that's negative 2. Square it, I get 4, so I'm going to add 4 to both sides. So I get negative 64 on the left, and on the right, this is the perfect square. This is lambda minus 2 squared. All right, so we take the square root of both sides, and I get plus or minus 8i on the left, and then we just need to add 2 to both sides. So I get lambda is 2 plus or minus 8i. And we need the eigenvalues. I'm sorry, these are the eigenvalues. I need the eigenvectors. So let's find an eigenvector for lambda equals 2 plus 8i. So I need to solve this equation. I need to solve a minus 2 plus 8i times identity I times x equals 0. What this means is I'm going to subtract 2 plus 8i from the main diagonal of A. This is A, right? This is our coefficient matrix. I'm going to augment with 0 and then solve for the x vector. So I'm going to subtract 2 minus lambda from the main diagonal. Sorry, 2 plus 8i from the main diagonal. And then augment with 0 vector. And now we're going to row reduce and solve the system. So just a little simplification here. So 3 minus 2 is 1. So I get 1 minus 8i. Then 1 minus 2 would be negative 1. And then minus 8i. So one thing we could do would be to multiply the first row by the complex conjugate of 1 minus 8i. So it would be 1 plus 8i. So we could say replace row 1 with 1 plus 8i row 1, and that'll make this top left corner a real number that we can use 5 to eliminate maybe. So if we multiply 1 plus 8i times 1 minus 8i, I'm going to get 1 minus 64 I squared. I squared is -1. So I'm going to get 1 plus 64. This will be 65. This is minus 13 times 1 plus 8i. I have 5 and -1 minus 8i on the bottom. We can see that the first row is a multiple of the second row. So the first row is 13 times the second. So we can get rid of, let me change this equal sign here. We can get rid of one of these rows. And then I'm going to divide this row by 5. Right. So that is our row reduced matrix. So now let's find the eigenvector. So, we have basic variable and then we have a free variable. And we'll call it x1 and x2. So x1 is 1/5 plus 8/5 I times x2. If I solve this equation for x1, and then x2 is free. So if I want an eigenvector, I can use, if I let x2 be 5, that would cancel out these fractions. I would get 1 plus 8i and 5. All right. Now, turns out that's all I need. I just need this one vector with this one eigenvalue. I can turn this into 2 solutions. So let's get a new page here. So one of my solutions would be, say, e to the 2 plus 8i t times the eigenvector 1 plus 8i 5. Okay. Now we can write this as e to the 2t times e to the 8it times 1 plus 8i and 5. And we can use Euler's formula on the e to the 8ti. So that's going to be cosine of 8t plus I sine of 8t. So now I'm just going to multiply this cosine 8t plus I sine 8t inside the eigenvector. I still have this e to the 2t up front. So I get cosine 8t plus I sine 8t. That's this thing times 1. Then I also have to multiply by 8i. So I get 8i cosine 8t plus 8i squared. That's actually going to be minus 8, right? The I squared will be -1. So I get minus 8 sine 8t. And on the bottom, I get 5 cosine 8t plus 5i sine 8t. And because we have complex values, we can split this up into a real part and imaginary part, and that'll give us our 2 separate solutions. So I'm going to make 2 vectors that have a real part and an imaginary part. So the real part is just going to have the things up here that don't have an I. So it'd be cosine 8t minus 8 sine 8t. On the bottom, it'll be 5 cosine 8t. So this is my real part. Then my imaginary part will be the I sine 8t and the 8i cosine. I'm factoring out the I, so I don't need to write it here. And on the bottom, I have 5 sine 8t. So I can use these two vectors as my linearly independent vectors. So I'm going to say my solution x is C1, arbitrary constant, e to the 2t times the first vector, cosine 8t minus 8 sine 8t, and then 5 cosine 8t on this in the second component, and then C2 e to the 2t times the second vector. That's sine 8t plus 8 cosine 8t, and then 5 sine 8t on the bottom. All right. So that's the solution, but we also had an initial value. So let's apply the initial value and solve for these constants. So x of 0 was 816. And that's going to be equal to this x where I'm going to plug in 0 for t, right? So e to the 2t will give us e to the 0. So those will be 1. And then sine of 0 is 0. Those are going to go away. And the cosines of zeros will be 1s. So I'll get C1, and then cosine of 0 is 1. On the bottom, cosine of 0 is 1 times 5. I get 1, 5. And on the second one, 8 cosine of 0 will just be 8 times 1. And on the bottom here, I got sine of 0, 0. So that one's 0. Let's need to solve this equation. So I can augment these vectors with 8 and 16 and solve for C1 and C2. And if you row reduce this, I'm going to skip the steps here, but if you row reduce, you get 16/5 and 3/5. So that tells you C1, this one tells you C2. So now I just need to write my solution and simplify it. So x is C1, that's 16/5, e to the 2t, and then times that first vector, cosine 8t minus 8 sine 8t. And then on the bottom, it's 5 cosine 8t. And then plus C2 is 3/5. Still have e to the 2t, and then I have the second vector, sine 8t plus 8 cosine 8t, and then 5 sine 8t on the bottom. Right, so this actually can simplify, right? We can write this as one big vector. So let's do that. So let's keep the e to the 2t factored out, but I want to multiply the constants inside. I want to add these together. So here I've got 16/5 cosine 8t, and then 8 times 16 over 5, that turns out to be 128 over 5 sine 8t. Then on the bottom, that just reduces to 16 cosine 8t. And I'm going to add to this vector. So on the top, I've got 3/5 sine 8t, and then plus, looks like 24/5 cosine 8t. Now on the bottom, I have plus 5. No, it's not 5, right? It's 5 times 3/5. So it's plus 3. sine of 18. Right, so I can add some of these together. So cosines added together, what do I get? It's 24 plus 16 is 40. 40 over 5 is going to be 8. And then the sines, so negative 128 plus 3, that's negative 125. That's minus 25. And the bottom remains the same. All right, so that's pretty good right there. I mean, you could multiply the e inside as well. I'm just going to leave it like that. All right, I'll see you in the next one.